Hey folks, welcome to my C++ for Windows tutorial series. This is chapter 2, and what we're going to be doing this time around is a little bit more on the theoretical side. We're not going to be doing as much programming this time, but it's really important that you can understand these concepts because it'll just make everything else a lot easier later on. So we mentioned earlier in chapter 0/1 that computers only understand zeros and ones on or off, bits and bytes. So we're going to be looking at how exactly you can do that and how you can understand the system as well. And when you can do that, then you'll start understanding your code a lot more, and you can figure out ways to make it faster, make it work a lot better, or figure out exactly what it's doing behind the scenes. So we're going to start off by looking at the binary system. Then we're going to look at the hexadecimal system, and finally what bits are, what bytes are, and top it all off just by briefly looking at Ascii. So let's get right into it. I decided to drag out the old drawing tablet so we can start actually visualizing a few things. So we use a numbering system called the decimal system here. You've probably heard that since you were like in 2nd grade up to 4th grade, somewhere around there. And that essentially means we use the following digits in our counting. We use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many digits are here? We have a total of 10 digits. But 10 isn't one of these digits. 10 is actually 2 digits. And you're going to see this concept over here carries over quite a bit in pretty much every other system. Now, how do we count in our decimal system? Well, we go all the way up, 0 through 9. But once we hit 9, where do we go? Well, we have to carry that last digit over. We add 1 to the digit right beside it once it's all filled up. And if both of those digits are filled up, we create a new decimal spot right beside it for the hundreds. And basically the exact same concept works in binary as well, except in binary, we only have 2 digits, hence the bi in its name. We only have zeros, and we have ones. And we have 2 digits here. So let's try counting in binary real quick. We have 0, and what does 0 equal in binary? Well, it equals 0. We'll have 1, and this also equals 1. We're good so far? But we only have 2 digits, and that first digit we have here is filled up. So what do? Well, just like in our decimal system here, we fill up the digit here, and we just add 1 to the one beside it. So we're just going to do that. 1, 0, 10. And how much is that? That's equal to 2. So do you see what happened? We have 2 digits here. And 10 in binary is equal to 2. Similarly, how 10 in decimal is equal to 10, because we're using that system. But that 10 always seems to represent the actual base number, and that's a really neat little tip if you're ever wondering. So, let's keep going. We have 11, which is equal to 3. But now both of these digits are filled up again, because we only have 2 digits. So, we do the exact same thing, we just carry it over. We're at 100. And what's 100? 100 is equal to 4, because we're only going up by 1 each time. Now you can continue. Go 101 is equal to 5, 110 is equal to 6, but I'm not going to bore you with all of that. There's only one more pattern you need to realize, is that when we hit 10, that's equal to 2, but when we hit 100, that's equal to 4. Now, we have 10 digits in our system, so when we hit 10, well, that's a power of 10. When we hit 100, that's also a power of 10. And when we hit 1,000, that's another power of 10. and 10,000 and 100,000, a million, so on and so on. And the exact same concept is stuck here as well. You see, we hit 10, which is equal to 2, and 2 is a power of 2. It's 2 to the power of 1. And when we hit 100, we're at 4, and 4 is another power of 2. It's 2 to the power of 2. And when we hit 1,000 in the system, that'll be worth 8. And 8's another power of 2. It's 2 to the power of 3. It's 2 cubed. And we can keep going on forever, and that rule will always be the same. So before we get any deeper than that, let's look at the hexadecimal system. Now, hexa, deca, so 6 and 10. So it would be 16 digits. Except our system doesn't have 16 digits, so how do we represent the other 6 that are missing? Well, simple enough. We take the 10 that we already have, and a bunch of people decided that we'll just start substituting other symbols in its place. And I think you might recognize them, actually, if I write them out for you. So we have our 10, 0 through 9, and we have our 6, A through F, which adds up to 16. But notice, we go 9, and then A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. But when we add that 0 to it at the end, or at the beginning rather, we add up all the way to 16. So there's 16 digits here, but 16 is not one of them. And actually, if you were to write out 16 in hexadecimal, you would end up with 10, because that digit filled up, and then you add a 1 right beside it. So 16 is 10, just like we saw. 10 is 2 in the binary system. 10 is 10 in the decimal system. Now, let's start looking at those powers of 2 again, because they're very closely related with 16, because 16 is 2 to the power of 4. And this is a really good time to introduce the concept of bits and bytes. So essentially what the computer scientists did back in the day, they decided that 8 bits would be 1 byte, and one bit is equal to one of the digits in these numbers that we wrote out over here. 0, 1, 0, or any of these down here. Take a single one of those digits, and that is 1 bit. So 1 byte being a total of 8 bits could range anywhere from this number all the way to this number. Well, that's not right. There we go. 0 to 255. And what do you notice about this? Well, we take our 0 here, and we add it to the 255, and we get a total of 256 different numbers. And if you're paying attention, 256 is the square of 16. And sure enough, 4 bits is equal to 16 as well. Or rather, from 0, 0, 0, 0 to 1, 1, 1, 1. When we add that 0 to the 15, we get 16. So essentially, if you were to divide these two numbers right down the middle, you have groups of 4 bits, and each group there is equal to 1 digit in the hexadecimal system. So when we're writing out these numbers, we use a simple notation. We prefix number with 0x, and then we can write out our number. So it might be 0x00, it might be 0xFF, which is 255. Because 256 would be 0x100. And we only really use this hexadecimal system, so it's easier for us to read as people. We don't want to be going through some super long number, like let's say it was like 4 bytes long. So what's that? That's 32-bit. But we don't want to calculate 32 digits. Instead, we can just write it out as 0x and ABCD. That's a lot more easier to understand than it would be to read just the binary itself. Now, building off of these systems, we have a single byte, which is 8 bits here. And we have our hexadecimal system where 2 digits is equal to 1 byte as well. And this is where it gets really interesting with our Ascii system. Essentially, in the late 70s to around maybe mid-80s, somewhere in there, don't fact check me on this, but a bunch of computer scientists, they came up with this system to represent every character that could be used in a computer. Like all your letters, A through Z, uppercase and lowercase, all the numbers, all the special characters, like when you hit Shift 2 to make the @ symbol, all those, and all kinds of other symbols, like for accents in different languages and stuff like that. They actually managed to fit all of these characters into a single byte, which was represented numerically. And this was called the Ascii system. And if you look up online for ASCII table of some sort, you'll come across something that looks vaguely like this. And you can interpret this by reading what the decimal number is, and you'll see, well, this is only half of it. It goes up to 128. The extended ASCII is 1 full byte. But yeah, you'll see that, sure enough, you have your binary number, you have the hexadecimal number, you have your decimal number. And it even shows you which character it represents in that system. And even a lot of characters that you can't actually print, like the delete character, but it's technically a type of keystroke. It's a button press, so it's in there too. There's a lot of different characters like that. The line feed, or also known as when you hit enter, or the carriage return is when you hit enter on a Mac. And there's all sorts of different things, and you usually don't really need to know these, but it's important to know that this system exists, and this is the system that we're going to be using when we're doing all the programming. And when you write out your strings and all that, like the hello world we did, that's written in ASCII. It's very important that you know that. So, for the next lesson, we're going to start getting into different data types. We're going to look at the integers, like we did in Chapter 1. We're going to look at the strings, like the hello world we wrote in Chapter 1. We're going to look at just individual characters, and we're going to look at all kinds of different things. So, yeah, get ready for it, get excited, and I will see you guys in Chapter 3. Peace out.